Hi. Today I will discuss how to simulate bivariate normal random variables. So what we'll do is we'll take two normal random variables with two random variables, which are x and y, which have a joint density, and they'll be individually normal, and we'll have some dependency among them. So we discussed as an example last time. We had said that x and y was a two random variables with joint PDF given by f of x y is equal to root 3 by 4 pi e to the minus 1/2 x squared minus xy plus y squared. So this turned out, in the sense that I called this bivariate normal. I didn't explain to you why. It turned out that if you compute the marginal density of x, which is like fxx is fxy dy and integral over y, we found out that after completing the square, which is given in pink, we found out that it was like normal 0, 3, 4, 3, 4 by 3. That means mean 0 and variance 4 by 3. So then what we did was, we have noticed that fxy was symmetric in x and y. So it means fxy was fyx. So the density of y should be the same, because if I integrate x with f with respect to y, same integrating with respect to x. So y also turned out to be normal 0, 4 by 3. Sorry about that. So then we decided that we checked immediately that the random variables were not independent. That is, fxx times fyy was not equal to fxy, because if you just check the formula, it's not quite correct, because fyy is this, fxx is this, and you look at fxy, it's a complicated expression. It will not be the same. So once we do this, we know that they're not independent. We also verified another way of non-independence. We looked at the conditional density of y given x equal to x. So this turned out, if you do the calculation of fxy by fxx, if you do the whole calculation, it turned out that y given xx was equal to normal with mean x by 2 and variance 1. So x changes, y given x equal to x, mean also changes. So from this, I motivate for you the example. I said, okay, in general, you'll define a bivariate normal random variable in this fashion. So you will say, so x and y have bivariate density normal with parameters mu1, mu2, sigma 1 squared, sigma 2 squared, and rho, if it has the following joint density given by this expression right here. Now the thing is that the term sigma 1, sigma 2, mu1, mu2 have certain meanings. Mu1 happens to be the mean of x variable, mu2 happens to be the mean of y variable, sigma 1 squared is the variance of x, sigma 2 squared is the variance of y, and rho is the correlation coefficient between x and y. So now if I know mu, sigma 1, sigma 1 squared, rho, mu2, sigma 2, I know the entire density of x and y, joint. And one thing you can observe, to understand rho, I only need to know the covariance, because I already know sigma 1 squared, sigma 2 squared. If I know the covariance, I can come back and find out rho. So to identify the joint density of bivariate normal, you need to know the means, the two variances, and the covariance. So now I'll go and tell you how to simulate bivariate normal from this. Before that, let's just quickly recall a couple of things. So one thing to do is you can go and compute the mu1, mu2 in the example. Like I said, mu1 will be 0, mu2 will be 0, sigma 1 will be 1, sigma 2 will be 1, and rho will be 1/2. You can check that for the example. And you can also verify from the density that I've given you, if you integrate out x or integrate out y, you will end up getting x to be normal with mean mu1 and variance sigma 1 squared, y to be normal with mean mu2 and variance sigma 2 squared. And the correlation of x and y will be rho. Okay. So then, just to summarize, what we're going to do next is, to simulate bivariate normal variables, we must give them 5 parameters: the two means, the two variances, and the covariance. Okay, which is what we'll do now next. So I've written a simple R code to do this. I've done it in two ways. So let me clean up the R code a little bit. Start again. Let me clean everything up. So it's in two ways. So the first way is I've used the mass package. In the mass package, I simulate bivariate data using the mv-norm function. So let's just check what mv-norm does. mv-norm. So mv-norm. So if you look at it on the left hand side, it doesn't come. Interesting. Oh, mv-r-norm. Sorry about that. mv-r-norm. So it tells you that mv-r-norm will simulate from multivariate normal distribution. It will simulate with mu, sigma. So as long as you give mu as the mean vector, which I have specified to be 0, 0 in this case. If I put sigma, which is the covariance matrix, which is this one, which is 5, 3, 3, 4. So let me just try and illustrate that for you. So I put mu here. So if I do mu, I get 0, 0, the two mean vector is mu, and look at the variance covariance matrix, that's here. So sigma is essentially this variances are 5 and 4, and the covariance is 3. Okay. So now I have simulated 100 samples from multivariate normal, right? So now if I go here, I do this head data set and I give the first 6 rows of the bivariate data set, and tail means I get the last 5 rows. So you can do various things with it. Some exercise you can try is you can try to do a histogram of the x variable, histogram of the y variable to see if it's actually normal. You can check that, and so on and so forth. Now the next thing I want to do is I want to show you how the density looks like. So if you look at the form of the density, it's f of xy equal to e to the minus x squared, then y squared term is there and x squared term is there. So I want to show you how the surface plot looks like. So for this, we will use a package called mnormt. Mnormt is not necessary, but mnormt will just give you another way of plotting the density function, finding the density. So let me use mnormt. Then I create an x variable, which is minus 3 to 3, and y variable, which is minus 3 to 3 again. So I look at xy in this box. I take the mean to be 0, 0. I take sigma to be again the variance same variance coefficient as the previous one. And f computes the dm norm. So dm norm just computes the density function of the multivariate normal random variable. Let me just check this for you. So if you look at this, it just computes the dm norm is the density function of the multivariate normal random variable. You specify the mean vector and the variance covariance matrix, which is what I've done here. Now z, I just create a vector of x, y, and f, the 3-dimensional vector. Then here I'm just including packages to plot the scales. You get the scales of the Veridis function, and the Veridis is the color scheme that I like to use. Plot 3D is the one that I use to plot the function. So first I'll plot the level sets. So you plot the level set, you see the level set there. It's 0.05 in the middle, and then decreases to 0.005 towards the end of that. That's how the function will be large in the middle and then go down slowly as it goes far away from that. So let's just do a color plot of the 3D plot of this. So the first 3D plot I'll do is the one like this. So you can see the function. It's like really high in the middle and then goes down to, so at 0, 0 is here. So 0, 0 is right here. So it's very, very high. And it comes down, it decays quite quickly as you go towards 3. So in Percept 3D, you can use theta and phi, these two thetas and phis, to view it along various axes. You can check the help menu to see what exact axis you're viewing it as. So here I'll view it from a little bit of the side, so you'll get a view like this. So something happened, I'm sorry about that. So it's something like this, I'll get a different view. If I do 45, I get another view from the side, 60 from the little bit on the top, and then 90 all the way at the top. So this sort of concludes a simple code of how to simulate bivariate normal data first, the first part. The second part tells you how to plot a density function. So you can also, you can replace this point here by density function of any other multivariate distribution, and it will plot the whole thing. So that concludes this section on how to simulate bivariate normal data. I'll leave this code here, you can play with it a little bit. Thank you.